Hello physics students, this is Dr. Brenzi here. This is the first video for lesson 2.1.3, and our objective in this video, in this lesson, is that we will be able to use free body diagrams and Newton's second law to calculate force and acceleration. Okay, I'm going to assume that you have your notes, but if you don't, take a moment to pause the video and grab your notes. So, solving problems with Newton's second law kind of involves this set of steps right here, and it is kind of a long list, but once you see me do a couple of examples, I think you'll quickly get the hang of it, and you might not even need to refer to this list, but I thought I'd put it up here just as a guide for your first few problems. So usually when you want to solve second law problems, it is that you want to draw a free body diagram, and we practiced that in lesson 2.1.2. So if you don't remember how to do that, or if you need a little refresher, go ahead and go to that lesson's videos and browse at your leisure. So after you draw in your free body diagram, you're going to choose a coordinate system. So you're going to choose which direction is positive and which direction is negative, or you might have to choose which direction is x and which direction is y. And usually what ends up happening, most people just use conventional coordinate systems, so your positive is to the right and your negative is to the left. Or if you're going up and down, your positive is up and your negative is down, just like a regular coordinate grid would be. Next step you're going to want to do is you're going to want to write out Newton's second law, which is that the net force is equal to mass times acceleration. And it's always a good idea to make sure that you are writing this out using vector notation, because sometimes you actually have to separate the x direction from the y direction. Just like we had to separate x and y direction when we were solving trajectories. If you know the direction of the acceleration, if that's given to you in the problem, then it's also a good idea to draw that vector to the side of your free body diagram. You don't want to include it in your free body diagram, but you want to draw it off to the side, and I'm going to give you a demonstration of that when we get to our examples here. Finally, what you do then after that is you plug in your known values, and then we need to solve for unknown value, whatever that might be. So let's go through a couple of examples here. So the first example I have here is a 740 kilogram elevator. Says it accelerates upward at 1.1 meters per second squared, pulled by a cable of negligible mass. Find the tension force in the cable. Now, before I begin, I'm going to quickly talk about this little phrase right here, pulled by a cable of negligible mass. Why is that important? Well, it turns out to be important because if the cable doesn't have negligible mass, then you have to start thinking about, the upper parts of the cable pulling on the lower parts of the cable, and it just becomes very messy quickly, and it's a really advanced topic. So we're going to always assume that our cable is of negligible mass unless the problem states otherwise. So let's go ahead and try to find the tension force in this cable. So the first step that I listed is to draw a free body diagram, so let's go ahead and do that. We're going to use a dot to represent our elevator, and it seems like the forces that are at work are some sort of tension force pulling up, and we have also a force of gravity pulling the elevator down. All right. Now what I need to do is I forgot my second step here. Okay, choose a coordinate system, right. I knew I was forgetting a step there. So we are going to choose up as positive. Okay, and we're going to choose down as negative. And since we're only dealing with up and down, we don't need to actually worry about the left and right direction, so we don't need to worry about X and Y. So that's my coordinate system. All right, so now I'm going to write out F net, and let's include our vector on top, equals mass times the acceleration vector. Okay. Now it says that the acceleration is happening upward at 1.1 meters per second squared. So what I'm going to do, let me actually move this a little bit over so that I can include an acceleration vector right here. So I'm going to write F net equals mass times acceleration. Now let's go ahead and start plugging in what we know. We know that the acceleration is 1.1 meters per second, and that's in the upward direction. So I'm going to write 1.1 right here for my acceleration. My mass is 740 kilograms. So let's write 740 right there. Yep, and my little dot, my little multiplication symbol. Let's get that back. That is going to equal my net force. Now, what is the net force? Well, the net force is our tension force, so F sub T, and then it's going to be minus F sub G because that is acting in the negative direction, and that's why I put a minus sign there. Okay, so we don't know what the tension is. That's what we're trying to find out. We do know what the force due to gravity is. That ends up being 740 times 9.8. Now, why did I not write negative 9.8? Well, it's because I've already accounted for that negative direction out here with the force, so I don't need to actually include it there with the acceleration due to gravity. And then we're going to set that equal to 740 times 1.1. And when I do that, I'm going to get and solve for my tension force. I'm going to get a tension force equal to something like, see, 740. It's like 740 times about 11. So 740, so that seems to be 814 newtons. But since we only have two significant figures, we're going to round that to 810 newtons. All right. So that tension force that in the cable happens to be 810 newtons. All right, let's go through one more example. So here's another problem where we have two boys who are pushing an 8-kilogram box on a frictionless floor. Mike pushes the box to the right with a force of 15 newtons, while Carlos pushes the box 18 newtons to the left. What is the magnitude and direction of the box's acceleration? All right, so let's go through our steps here. Let's write out our free body diagram. So here we have our box. Let's see, Mike is pushing it to the right, 15 newtons. And Carlos is pushing it to the left, 18 newtons. Okay. And let's establish that left is a negative direction, right is the positive direction. Let's go ahead and write our Newton's second law, F net equals mass times acceleration. Right. And let's see here, our net force is going to be 15 newtons plus negative 18 newtons because this is pulling to the left. So we have 15 plus negative 18 equals the mass of the box, which is 8 kilograms, times the acceleration. Okay. Okay, well, this should be a pretty straightforward equation to solve. Whoa, and I suddenly lost my... There we go. So let's go ahead and solve this. So on the left-hand side, we have 15 plus negative 18, that is negative 3, equals 8 times A. And of course, I solve this by dividing both sides by 8. And we get our acceleration. Our acceleration equals negative 0.375 if you want to convert it to decimal. And that would be in units of meters per second squared, since it's acceleration. Okay, now if I am going to insist on using the correct significant figures, well, that only has one significant figure. That's the least number of significant figures. So if I want to be accurate in my sig figs, I better report that this is negative 0.4 meters per second squared. All right. All right, so that is how I would find the acceleration. So what is this telling me? It's telling me that this box is accelerating by 0.4 meters per second squared. In which direction? Well, it's the negative direction, so it's being accelerated toward the left. All right, physics students, hoping you find this video helpful. There are also going to be some examples tomorrow that we're going to work on, and once we have those examples on this video, I'll include those in another video, and we'll hopefully meet very soon. All right, have a good night. Bye. Oh, God.